By the way, I am Klein Paosanos, your reporter for today. Good afternoon, classmates. Good afternoon, sir. My topic for today is all about homomorphisms of groups. So in this section, we consider certain mappings between groups. These mappings will be defined in such a way as to preserve the algebraic structure of groups involved. More precisely, suppose we are given a function f from a group G into a group G sub 1, where star 1 denotes the operation of G sub 1. Let A be an element of G. Then under f, A corresponds to f of A. Then B corresponds to f of B. And A star B to f of A star B. So, if f is to preserve the operations of G and G sub 1, so A star B must be corresponds to f of A star 1, f of B. Since f is a function, this forces the requirement that f of A star B is equal to f of A star 1, f of B. So when we're going to say homomorphisms, a homomorphism is a structure preserving map between two algebraic structure of the same type, such as two groups, two rings, and two vector spaces. A group homomorphism is a map between two groups. In the definition 5.1.1, let G star and G sub 1 star 1 be groups and f a function from G into G sub 1. Then f is called a homomorphism of G into G sub 1 if for all A, B is an element of G. F of A star B is equal to A A of A star 1 F B, since we are going to preserve the operations of G and G sub 1, so it must be F of A star B is equal to F of A star 1 F of B. So that's why. So let the identity element of the group G sub 1 be denoted by E sub 1. Define the function of G into G sub 1 by f of A is equal to E sub 1 for all A is an element of G. Since f is f of A star B is equal to E sub 1 is equal to E sub 1 star 1 E sub 1 is equal to f of A star 1 f of B for all A B is an element of G. We find that f is a homomorphism from G into G sub 1. Okay. So this shows that there always exists a homomorphism from a group G into a group G sub 1. This homomorphism is called the trivial homomorphisms. The identity map from G onto G is also a homomorphism. In the theorem 5.1.2, let f be a homomorphism of a group G into a group G sub 1. Then 1 is if A E is equal to E sub 1. Then number 2 is if f of A raised to the negative 1 is equal to f of A raised to negative 1 for all A is an element of G. If H is a subgroup of G, then f of H is equal to f of H such that H is an element of G, is a subgroup of G sub 1. Number 4, if H of H sub 1 is a subgroup of G sub 1, then the inverse function of H sub 1 is equal to G is an element of G such that f of G is an element of H sub 1 is a subgroup of G and fH sub 1 is a normal subgroup, then the inverse function of H sub 1 is a normal subgroup of G. If G is number 5, if G is commutative, then f of G is commutative. Number 6, if A is an element of G is such that function composition of A is equal to n, then the function composition of f of A divides n. Proof. Since f is a homomorphism, f of E is equal to f of E is equal to f of E is equal to f of E sub 1. So this implies that f of E is equal to E sub 1 by the cancellation law. Number 2, let A is an element of G, then f of A is equal to f of A raised to negative 1 is equal to f of A negative raised to negative 1 is equal to f of E minus epsilon E A sub 1. Similarly, f of A negative 1, f of A is equal to E sub 1. Since f of A has a unique inverse, f of A raised to negative 1 is equal to f of A raised to negative 1. So, in the definition 5.1.3, let F be a homomorphism of a group G into a group G sub 1. The kernel of F, written ker F, is defined to be the set ker F is equal to A is an element of Number 3. Let H be a subgroup of J, then E is an element of H, and by in the number 1, f of E is equal to E sub 1, thus E sub 1 is equal, epsilon, E sub 1 is equal to f of E is an element of f of H, and so f of H is not equal to empty. Dili siya null set. Let f of A is equal to, let f of A, f of B is an element of f of H, where A and B is an element of H. Since H is a subgroup, the inverse of EB is an element of H. Thus, f of A, f of B is equal to f of A, f of B, negative 1 is equal to f of AB, negative 1 is an element of f of H. Hence, by theorem 4.1.3, f of H is a subgroup of G sub 1. Number 4, by the number 1, E is an element of inverse function of H sub 1, and so the inverse function of H sub 1 is not equal to empty. Let AB is an element of the inverse function of H sub 1. Then f of A, f of B is be an element of H sub 1. Thus, by theorem 4.1.3, the inverse function of H sub 1 is a subgroup of G. Suppose H sub 1 is a normal subgroup of G sub 1. Let G is an element of G. We now show that G, the inverse function of H sub 1, G negative 1 is an set. So H sub 1 is a normal subgroup of G sub 1, and f of b is an element of H sub 1. Hence A is an element of the inverse function of H sub 1, and this shows that G, the inverse function of H sub 1, G negative 1, is a set of inverse function of H sub 1. Thus the inverse function of H sub 1 is a normal subgroup of G. Then in number 5, suppose G is a commutative. Let f of A, f of B is an element of f of G. Then f of A, f of B is equal to f of AB is equal to f of B A is equal to f of B, f of A. Hence, f of G is commutative. So, bisan pag bali-balihon mo na siya dira, basta kay nara na silang duha, okay ra. Number 6, since f of A raised to n power is equal to f of A raised to n is equal to f of E is equal to E sub 1, we have function composition of f of A divides n by theorem 2.1.28. In the definition 5.1.3, let f be a homomorphisms of a group G into group G sub 1. The kernel of f written by char f is defined to be the set kernel of f is equal to A is an element of G such that f of A is equal to E sub 1. By theorem 5.1.2, E is an element of kernel of f. Example 5.1.4. Define the function f from G plus into G sub n plus n by f of A is equal to A for all A is an element of G. From the definition of f, it follows that f maps G onto G sub n. Let AB is an element of Z. Then f of A plus B is equal to the cardinality of A plus B. Cardinality ba? Set A. I mean f of A plus B is equal to A plus B is equal to A plus N. B is equal to f of A plus N, f of B. Ano siya? So thus f is a homomorphism of Z onto Z sub n. Now kernel of f is equal to A is an element of Z such that f of A is equal to 0. A is an element of Z such that A is equal to 0. A is an element of Z such that A is divisible by n. A is an element of Z is equal to A is equal to Q, and for some Q is an element of Z. Qn such that Q is an element of Z. Example 5.1.5. The groups Z sub 4 plus Z sub 4 and Z sub 8 plus Z sub 2 are commutative and each is of order 16. Suppose there exists a homomorphism of f of Z sub 4 cross Z sub 4 onto Z sub 8 cross Z sub 2. Now A is equal to 7 and 0 is an element of Z sub 8 cross Z sub 2, and function composition of A is equal to 8. Since f is onto Z sub 8 cross Z sub 2, there exists B is an element of Z sub 4 plus Z sub times Z sub 4 such that f of b is equal to a. By theorem 5.1.2 in the number 6, the function composition of f of b divides the function composition of b. Since the function composition of b, this is a contradiction. Hence, there does not exist any homomorphisms from z sub 4 cross z sub 4 onto z sub 8 cross z sub 2. Definition 5.1.6. Let G and G sub 1 be groups. A homomorphisms function G into G sub 1 is called an epimorphism if F is onto G sub 1, and F is called a monomorphism if F is 1 to 1. So we can call epimorphisms if F daw kay onto. If 1 to 1, we can call it monomorphisms. Mura na kalahian nila. So, again, if epimorphisms, this is onto. And then, if we're going to say monomorphisms, this is a 1-to-1 function. So, if there is an epimorphism F from G onto G sub 1, then G sub 1 is called a homomorphic image of G. So, example 5.1.7. Let R star be the group of all non-zero real numbers under multiplication. Define the function of R star onto R star 1 by f of A is equal to A. Now, f of AB is equal to AB is equal to AB is equal to f of A, f of B, which implies that f is a homomorphism. Since f of 1 minus 1 minus f of negative 1 and 1 is not equal to negative 1. So, f is not 1 to 1. Also, from the definition of f, it follows that if f is not onto the R star, hence f is neither an epimorphism nor a monomorphism. So again, epimorphism if this is onto, and monomorphisms if it is 1-to-1 function. Theorem 5.1.8. Let F be a homomorphism of a group G into a group G sub 1. Then F is 1-to-1 if and only if kernel of F is equal to E. Proof. Suppose F is 1-to-1. Let A is an element of kernel of F. Then f of A is equal to E sub 1 is equal to f of A by theorem 5.1.2. Since f is 1-to-1, we must have A is equal to E. Hence, kernel of f is equal to E. Conversely, suppose that kernel of f is equal to E. Let A be an element of G. Suppose f of A is equal to f of B, then f of AB raised to negative 1 is equal to f of A, f of B raised to negative 1 is equal to f of A, f of B to negative 1 is equal to E sub 1. Thus, AB negative 1 is an element kernel of f is equal to E, and so AB raised to negative 1 is equal to E. So that is A is equal to B. This proves that f is 1-to-1. Okay. In theorem 5.1.9, Let F be a let F be a homomorphism of a group G into G sub 1. Then kernel of F is a normal subgroup of G. So, we have ganang proof here. Since E is an element of kernel of F is not equal to empty set. Let A be an element of kernel of F, then F of AB raised to negative 1 is equal to F of B negative 1 is equal to F of B is raised to negative 1 is equal to E sub 1 of E sub 1 negative 1 is equal to E sub 1 is equal to E sub 1. Thus AB raised to negative 1 be an element of kernel of F, and hence kernel of F is a subgroup of G by theorem 4.1.3. Let A be an element of G and H be an element of kernel of F, then F of A negative 1 is equal to F of A, F of H, F of A negative 1 is equal to F of A, F of H, F of A is negative 1 raised to negative 1 is equal to F of A E sub 1, F of A negative 1 is equal to E sub 1. Therefore, AHA is AHA raised to negative 1 is an element of kernel of F. This proves that A kernel of F A negative 1 is set of kernel of F. Hence, kernel of F is a normal subgroup of G by theorem 4.1.3. In example 5.1.1, consider S sub 3 and the normal subgroup. H is 1 2 3 1 2 3 and then 1 2 3 2 3 1 1 2 3 3 1 2. Define the function of S sub 3 into S sub 3 divides H by for all R. Pi is an element of S sub 3 F of R is equal to R H, then F of pi function composition of pi prime is equal to pi function composition of pi prime is H is equal to pi H. The function composition of R prime H is equal to F R function composition of F of R for all pi R pi prime is an element of S sub 3. Hence, F is an homomorphism. Also, kernel of F is equal to A is an element of E sub 3 such that AH is equal to H equals A sub A is an element of S sub 3 such that A is an element of H is equal to H. So, that's all. I guess naramoy na sabtan, guys. And then thank you for listening and God bless everyone. Stay safe. Bye.